Class 12th Chemistry, Chapter 1 The Solid State. From our earlier studies, we know that liquids and gases are called fluids because of their ability to flow. The fluidity in both these states is due to the fact that the molecules are free to move about. On contrary, the constant particles in solids have fixed positions and can only oscillate about their mean positions. This explains the rigidity in solids. These properties depend upon the nature of the constituent particles and the binding forces operating between them. The correlation between the structure and properties helps in the discovery of new solid materials with desired properties. For example, carbon nanotubes are new materials that have potential to provide a material that are tougher than steel, lighter than aluminum, and have more conductive property than copper. Such materials may play an expanding role in the future development of science and society. Some other materials which are expected to play an important role in future are high temperature superconductors, magnetic material, biodegradable polymers for packaging, biocompliant solids for surgical implants, etc. Thus the study of this state becomes much more important in the present scenario. In this unit, we shall discuss the different possible arrangements of particles resulting in the several types of structures and explore why different arrangements of structural units lend different properties to the solids. We will also learn how these properties get modified due to the structural imperfections or by the presence of impurities in minute amounts. That was the introduction, and now we move on to general characteristics of solid state. In class 11th, you have learned that matter can exist in three states, namely solid, liquid, and gas. Under a given set of conditions of temperature and pressure, which of these would be the most stable state of the given substance depends upon the net effect of two opposing factors. These are intermolecular forces which tend to keep the molecules or atoms or ions closer, and the thermal energy which tend to keep them apart by making them move faster. At sufficiently low temperature, the thermal energy is low and the intermolecular forces bring them so close that they cling on to one another and occupy fixed positions. These can still oscillate about their mean positions and the substance exists in solid state. The following are the characteristic properties of the solid state. There are 4 properties of the solid state. That's what's important in this part. They have definite mass, volume, and shape. Intermolecular distances are short. Intermolecular forces are strong. Their constituent particles, atoms, molecules, or ions have fixed positions and can only oscillate about their mean position, and they are incompressible and rigid. Now, there are mainly 2 types of solids that are amorphous and crystalline, and that is discussed in the next section. Amorphous and crystalline solids. Solids can be classified as crystalline or amorphous solids on the basis of the nature of order present in the arrangement of their constituent particles. A crystalline solid usually consists of a large number of small crystals, each of them having definite characteristic geometrical shape. The arrangement of constituent particles, atoms, molecules, or ions in a crystal is ordered and repetitive in 3 dimensions. If we observe the pattern in one region of the crystal, we can predict accurately the position of the particles in any other region of the crystal, however far they may be from the place of observation. Thus, crystal has a long-range order, which means that there is a regular pattern of arrangement of particles which repeat itself periodically over the entire crystal. Sodium chloride and quartz are typical examples of crystalline solids. Glass, rubber, and many other plastics do not form crystals. When their liquids solidify on cooling, these are called amorphous solids. The term amorphous comes from the Greek word amorphos, meaning no form. The arrangement of constituent particles, atoms, molecules, or ions in such a solid has only a short-range order. In such an arrangement, the regular and periodically repeating pattern is observed over short distances only. Regular patterns are scattered, and in between the arrangement is disordered. The structure of quartz, crystalline, and quartz glass amorphous are shown in figure 1.1 A and B respectively. While the two structures are almost identical, yet in the case of amorphous quartz glass there is no long-range order. The structure of amorphous solids is similar to that of liquids. Due to the difference in the arrangement of particles, the two types of solids differ in their properties. Now, nextly, the properties of crystalline and amorphous solids are discussed in the next paragraph. Crystalline solids have sharp melting point. At characteristic temperature, they tend to melt abruptly and become liquid. On the other hand, amorphous solids soften, melt, and start flowing over a range of temperature and can be molded and blown into various shapes. Amorphous solids have same structural features as liquids and are conveniently regarded as extremely viscous liquids. They may become crystalline at some temperature. Some glass objects from ancient civilizations are found to become milky in appearance because of some crystallization. Like liquids, amorphous solids have a tendency to flow, though very slowly. Therefore, sometimes these are called pseudo-solids or supercooled liquids. Amorphous solids are isotropic in nature. Their properties such as mechanical strength, refractive index, and electrical conductivity, etc. are same in all directions. It is because there is no long-range order in them and the arrangement of particles is not definite along all the directions. Hence, the overall arrangement becomes equivalent in all directions. Therefore, value of any physical property would be same along any direction. Crystalline solids are anisotropic in nature, that is, some of their physical properties like electrical resistance or refractive index show different values when measured along different directions in the same crystal. This arises from different arrangement of particles in different directions. This is illustrated in figure 1.2, which you can see to the left side of the paragraph. That is anisotropy in crystals due to different arrangement of particles along different directions. Okay, this figure shows a simple two-dimensional pattern of arrangement of two kinds of atoms. Mechanical properties such as resistance due to sharing stress might be quite different in two directions indicated in the figure. Deformation in CD direction displaces row which has two different types of atoms, while in AB direction rows are made up of one type of atoms and are displaced. One type of atoms are displaced. The differences between the crystalline solid and the amorphous solid are summarized in the next table, that is table 1.1. We can read that. The distinction between crystalline and amorphous solid. This table is what's important from this part. Shape. Definite characteristic and geometrical shape is for crystalline solids. First we'll read the part of crystalline solids and then we'll move on to amorphous solids. Shape. For crystalline solids, definite characteristic and geometrical shape. Melting point for crystalline solids are melted sharp and characteristic temperature. Cleavage property. When cut with a sharp-edged tool, they split into two pieces and the newly generated surfaces are plain and smooth. Heat of fusion. They have definite and characteristic enthalpy of fusion. Anisotropy. They are anisotropic in nature and are true solids. Order in arrangement of constant particles are long-range order. Now for amorphous solids, they have irregular shape. They gradually soften over a range of temperature. When cut with a sharp-edged tool, they cut into two pieces with irregular surfaces. They do not have definite enthalpy of fusion. They are anisotropic in nature, pseudo-solids or supercooled liquids, and are of short-range order. Now we'll compare the two and read once again. The shape for crystalline solids have definite geometrical shape, whereas amorphous solids have irregular shape. Melting point. Crystalline solids melt at sharp characteristic temperature, whereas amorphous solids gradually soften over a range of temperature. The cleavage property. When cut with a sharp-edged tool, they split into two pieces and the newly generated surfaces are plain and smooth for crystalline solids, whereas for amorphous solids, when cut with a sharp-edged tool, they cut into two pieces with irregular surfaces. The heat of fusion. They have definite and characteristic enthalpy of fusion for crystalline solids, and for amorphous solids, they do not have definite enthalpy of fusion. Anisotropy for crystalline solid is that they are anisotropic in nature, whereas for amorphous solids it is isotropic in nature. The nature are for crystalline solids they are true solids, whereas for amorphous solids they are supercooled liquids or pseudo-solids. Supercooled liquids or pseudo-solids. Order in arrangement of constituent particles. Its long-range order for crystalline solids and its short-range order for amorphous solids. Polycrystalline solids. Before that, just clearing that cleavage property means when cut with a sharp-edged tool and they split into two different parts. That's called cleavage property. Polycrystalline solids. Besides crystalline and amorphous solids, there are some solids which apparently appear amorphous but have microcrystalline structures. These are called polycrystalline solids. This part is not much important, but we'll just read it. Metals often occur in polycrystalline condition. Individual crystals are randomly oriented, so a metallic sample may appear to be isotropic even though a single crystal is anisotropic. That's what a polycrystalline solid is. Applications of amorphous solids are useful materials. Example like glass, rubber, plastic find many applications in our daily life. These applications are elaborated later on in detail, but for now this is just a gist of the applications. Now we have in-text questions. Why are solids rigid? It's because of the physical properties. Why do solids have definite volume? Because the particles are not allowed to move much about, so they have a definite volume. Now classify. These questions we can take on later on. Now moving on, classification of crystalline solids. Okay, in section 1.2 we have learned about the amorphous substances and that they have only short range order. However, most of the solid substances are crystalline in nature. For example, in all the metallic elements like iron, copper and silver, non-metallic elements like sulfur, phosphorus and iodine, and compounds like sodium chloride, zinc, sulfide and naphthalene form crystalline solids. Crystalline solids can be classified in various ways. The method depends on the purpose in hand. Here we will try to classify crystalline solids on the basis of nature of intermolecular forces or bonds that hold the constituent particles together. These are 1. Van der Waals forces, 2. Ionic bonds, 3. Covalent bonds and 4. Metallic bonds. On the basis of crystalline solids are classified into 4 categories, viz. Molecular, ionic, metallic and covalent solids. Let us learn about these categories. So this is an elaborate part of the 4 types of amorphous crystalline solids, but there is a gist for this in a table. Next, we'll just read this part and then move on to the table. The table is what's important and it gives all the information that you need to learn throughout all these separate points. So firstly, they have elaborated every single type of solid as a paragraph model, and then next they have it in a table. The table is much easier to study. It's your personal choice. Now reading the paragraph part. Molecular solids. Molecules are constituent particles of molecular solids. Molecules are constituent particles of molecular solids, which is obvious, and these are subdivided into 4 categories. There are non-polar molecular solids, polar molecular solids and hydrogen bonded molecular solids. So non-polar molecular solids, they comprise either of atoms, for example argon and helium, or the molecules formed by non-polar covalent bonds, for example hydrogen H2, Cl2 and I2. In these solids, the atoms or molecules are held by weak dispersion or London forces, about which you have learnt in class 11th. These solids are soft and non-conductors of electricity. They have very low melting points and are usually in liquid or gaseous state at room temperature and pressure. Polar molecular solids. The molecules of substances like HCl, SO2, etc. are formed by polar covalent bonds. The molecules in such solids are held together by relatively stronger dipole-dipole interactions. These solids are soft and non-conductors of electricity. Their melting points are higher than those of non-polar molecular solids, yet most of these solids are gases or liquids under room temperature and pressure. Solids SO2 and solid NH3 are some examples of such solids. That's what's for polar molecular solids. And now we are moving on to hydrogen bonded molecular solids. The molecules of such solids contain polar covalent bonds between H and F, O or N atoms. Strong hydrogen bonding binds molecules of such solids like H2O, ice. They are non-conductors of electricity, and generally they are volatile liquids or soft solids under room temperature and pressure. Now moving on to ionic solids. In ionic solids, ions are the constituent particles, which is obvious, and such solids are formed by three-dimensional arrangement of cations and anions. That is, for ions there are cations and anions, and it is formed by three-dimensional arrangement. Ionic solids are formed by three-dimensional arrangement of its particles, that is cations and anions, bound by strong Coulombic, that is electrostatic forces. These solids are hard and brittle in nature. They have high melting and boiling points. Since they are brittle in nature, they have high melting and boiling points, and ions are not free to move about. They are electrical insulators in the solid state. However, in molten state, when dissolved in water, ions become free to move about and they conduct electricity. Ionic solids, they are mostly insulators in their solid state, but in their liquid state, the ions can freely move about and they become conductors of electricity. For the you can take NaCl for the example of an ionic solid. Now, metallic solids. Metals are orderly collection of positive ions surrounded by and held together by a sea of electrons. These electrons are mobile and are evenly spread out throughout the crystal. Each metal atom contributes one or more electrons towards this sea of mobile electrons. These free and mobile electrons are responsible for high electrical and thermal conductivity of metals. When an electrical field is applied, these electrons flow through the network of positive ions. Similarly, when heat is supplied to one portion of a metal, the thermal energy is uniformly spread throughout by the free electrons. Another important characteristic of metals is their luster and color in certain cases. This is also due to the presence of free electrons in them. Metals are highly malleable and ductile. Covalent or network solids. That's the last part, I think. A wide variety of crystalline solids of non-metals result from the formation of covalent bonds between adjacent atoms throughout the crystal. They are also called giant molecules. Covalent bonds are strong and directional in nature, therefore are held very strongly at their positions. Such solids are very hard and brittle. They have extremely high melting points and may even decompose before melting. They are insulators and do not conduct electricity. Example, diamond, silicon carbide, and graphite are typical examples of these such solids. Although graphite belongs to this class of crystals, but it is soft and a conductor of electricity. So graphite is an exception. Graphite belongs to covalent or network solid, but there is an exception, that is it is soft and it can conduct electricity, whereas other solids like diamond is really hard and it does not conduct electricity. So the exception in graphite is due to its typical structure. Carbon atoms are arranged in different layers and each atom is covalently bonded to 3 of its neighboring atoms in the same layer. The fourth valence electron of each atom is present between different layers and is free to move about. These free electrons make graphite a good conductor of electricity, and different layers can slide one over the other. This makes graphite soft, solid and a good solid lubricant. The different properties of 4 types of solids are listed in table 1.2, and this is the table that's important, and it explains everything that we just talked about in a gist. So different types of solids. There are mainly 3 types of solids, that are non-polar, polar and hydrogen bonded solids, molecular solids. These are 3 types of molecular solids. The constituent particles are molecules. The bonding or attractive forces are by dispersion or London forces or dipole-dipole interactions in polar, In non-polar, it is dispersion or London forces. In polar, it's dipole-dipole interaction. And in hydrogen-bonded molecular solids, it is hydrogen bonding. So examples for non-polar molecular solids are argon, calcium chloride, not calcium chloride, carbon chloride, CCl4, I think it's carbon chloride. Anyways, physical nature is soft. They are insulators, and they have very low melting points. Now for polar molecular solids, the examples are H2, I2, CO2, that's hydrogen, iodine, and carbon dioxide. They are physically soft in nature. They are they are insulators and have low melting point. For hydrogen bonded molecular solids, the examples are H2O, that's ice, not water. H2O is water, but it's in the ice form that's considered. The physical nature is hard, and the electrical conductivity is, they are insulators, and they have very low, so not very low, they have low melting points. The next type of solids are ionic solids. The constituent particles are ions. They have Coulombic or electrostatic forces bonding them. Examples are NaCl, MgO, ZnS, CaF. Physical nature, they are hard but brittle. And electrical conductivity, they are insulators in solid state, but they tend to be conductors in the liquid state. This is due to the free availability of free ions when they are dispersed in a liquid medium. So that's they are made in an aqueous solution. So the melting points are high for ionic solids, and for metallic solids, the constant particles are positive ions in a sea of delocalized electrons. That's what a metal looks like. And the bonding or attractive forces are by metallic bonding. The examples are Fe, Cu, Ag, Mg, etc. They are physically hard but malleable and ductile conductors in solid state as well as in molten state, and their melting points are fairly high. The last part is covalent or network solids. Atoms are the constituent particles of covalent or network solids. They are bonded by covalent bonds, and examples are SiO2, quartz, SiC, C diamond, and AIN, and C graphite. There are two C's, one for diamond and one for graphite. You should note that. Everything is hard except for graphite, that is soft. It's an exceptional case that we discussed just above. And usually covalent solids are insulators, but graphite is a conductor, again the exception, and their melting points are overall very high. To break the covalent bond, it takes really high energy. And now we have again in-text questions which we will discuss later on. The next part is crystal lattice and unit cells. You must have noticed that when tiles are placed to cover a floor, a repeated pattern is generated. If after setting tiles on a floor, we mark a point at the same location in all the tiles, example center of the tile, and see the marked positions, only ignoring the tiles, we obtain a set of points. We are discussing crystal lattices and unit cells, okay? This set of points is the scaffolding on which a pattern has been developed by placing tiles. This scaffolding is a space lattice on which two-dimensional pattern has been developed by placing structural units on its sets of points, that is tile in this case. So what it says is that if we put up a set of points by placing tiles, that is four edges, we put points on the four corners of a tile, and we make up a grid like that. And each point that we mark is a lattice point, and the structural unit is called basis or motif. The total structural unit, that is 4 points together, I think, no, 2 points, is called motif. I am actually not sure about this part. When motifs are placed on point in space lattice, a pattern is generated. In crystal structure, motif is a molecule, atom, or ion. A space lattice, also called a crystal lattice, is the pattern of points repeating the locations of these motifs. In other words, space lattice is an abstract scaffolding for crystal structure. When we place motif in the identical manner of points of the space lattice, we get a crystal structure. Figure 1.5 shows a motif, a two-dimensional lattice, and a hypothetical two-dimensional crystal structure obtained by placing motifs in two-dimensional lattice. Special arrangement of lattice points gives rise to different types of lattices. Figure 1.6 shows arrangement of points in two different lattices, lattice A and lattice B. In lattice A, we have it all aligned like we considered before, and in lattice B, it's 4 points like this, and in the second line, the first point starts from the middle of the first 2 points. So, in the case of crystalline solid space lattice is a three-dimensional array of points. The crystal lattice is obtained by associating structural motifs with lattice points. Each repeated basis or a motif has same structure and same spatial orientation as the other one in a crystal. The environment of each motif is same throughout the crystal except for its surface. Following are the characteristics of a crystal lattice. A. Each point in a lattice is called lattice point or a lattice site. B. Each point in a crystal lattice represents one constituent particle, which may be an atom, a molecule group of ions, or an ion. Lattice points are joined by a straight line to bring out the geometry of the lattice. We need only a small part of the space lattice of a crystal to specify crystal completely. This part is called unit cell. One can choose unit cell in many ways. Normally the cell is chosen which has perpendicular sides of shortest length, and one can construct entire crystal by transitional displacement of unit cells in 3 dimensions. Figure 1.7 shows the movement of unit cells of a 2-dimensional lattice to construct an entire crystal structure. Also, unit cells have shapes such that these fill by lattice without leaving space between the cells. In 2 dimensions, a parallelogram with a side length A and B at an angle R between the sides is chosen as a unit cell. Possible unit cells in 2 dimensions are shown in figure 1.8. So basically what I feel is a unit cell is a part of a crystal when placed repeatedly in a space lattice of the crystal that can form an entire crystal. Hope you understood. The next is a portion of 3-dimensional crystal lattice and its unit cell is shown in figure 1.9. That's to the top right corner of the textbook. A portion of 3-dimensional and its unit cell. A 3D unit cell is shown there. In 3-dimensional crystal structure, unit cell is characterized by the characterization of a unit cell in 3-dimensional structure is given. First, its dimensions along 3 edges A, B and C. These edges may or may not be mutually perpendicular. And the second one is angles between the edges alpha between B and C, beta between A and C, and gamma between B, A and B. Thus, a unit cell is characterized by 6 parameters. Those are A, B, C, alpha, beta and gamma. There is a table that explains this. That's coming below. Now we have primitive and centered unit cells. Unit cells can be broadly divided into 2 categories: primitive and centered unit cells. Primitive unit cells. When constituent particles are present only on the corner positions of a unit cell, it is called primitive unit cell. A centered unit cell is when a unit cell contains one or more constituent particles present at positions other than the corners in addition to those at the corners, is called a centered unit cell. A centered unit cell can be divided into like 3, I think. First one is body centered unit cell, BCC. Such a unit cell contains one constituent particle, atom, or molecule or ion at its body center besides the ones at its corner. The second one is face centered unit cell, and such a unit cell contains one constituent particle at the center of each face besides the ones at its corners. And the end centered unit cell, in which such a unit cell constitutes particle. Such a unit cell, one constituent particle is present at the center. One constituent particle is present at its center. of any two opposite faces besides the one present at its corner. Okay, once again, face center. Okay, body center unit cell, one constituent particle, atom, molecular, or ion at its body center besides the ones at its corner. One particle in its body and besides those at the corners. Face-centered unit cell is when one is unit cell that contains one constituent particle present at center of each face. There are one constituent particle at the center of each face besides the ones at its corners. And the end-centered unit cell is when is such a unit cell when one constituent particle is present at the center of any two opposite faces. One constituent particle present at the center of any two opposite faces, that is two constant particles are two opposite faces, those are opposite to each other besides those present at its corners. I hope what I'm telling is right. This is the first time I'm reading this. Okay, so the inspection of a variety of crystals leads to the conclusion that all can be regarded as conforming to one or the seven regular figures. Just a sec, let me confirm if I missed any things. So we have three types of centered unit cell, that are BCC, FCC and ECC. Now we are moving on to a description that they have given after that. Inspection of a variety of crystals leads to the conclusion that all can be regarded as conforming to one or the seven regular figures. These basic regular figures are called seven crystal systems to which a system or a given crystal belongs. It is determined by measuring the angles between its faces and deciding how many axes are needed to define the principal features of its shape. Figure 1.1 shows seven crystal systems: cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic and triclinic. These are the seven basic crystal systems that can be formed with all the information that we have, with the observations that we made from Lerner. A British mathematician Brevis showed that there are only 14 possible three-dimensional arrangements, and these are called Brevis lattices. So there are only 14 types of three-dimensional arrangement of dimensional lattice, three-dimensional lattices, and these are called Brevis lattices, which I'll discuss later on in a box. And now coming on, we have the table of the seven primitive unit cells and their possible variations as centered unit cells that we just talked about. So the first crystal system is cubic. The possible variations are primitive, body centered and face centered. The axial or edge lengths are A is equal to B is equal to C. The axial angles are alpha is equal to beta is equal to gamma, and totally is equal to 90 degree. Examples are NaCl, zinc blend, Cu. Tetragonal. For tetragonal, the possible variations are primitive, body centered. The axial distances or edge lengths are A is equal to B and is not equal to C. The axial angles are alpha is equal to beta is equal to gamma is equal to 90 degree. Examples: white tin, SnO2, TiO2, CaSO4. Next, the orthorhombic. The possible variations are primitive, body centered, face centered, end centered. The axial distances or edge lengths are A is not equal to B is not equal to C. Alpha is equal to beta is equal to gamma is equal to 90 degree. And rhombic sulfur, KNO3 and BaSO4 are the examples for orthorhombic. Now moving on to hexagonal. The possible variations are only primitive, and the axial distances or edge lengths are A is equal to B is equal to C. The axial angles are alpha is equal to beta is equal to 90 degree and gamma is equal to 120 degree. And the examples are graphite, ZNO, CDS. Rhombohedral or trigonal. The possible variations are primitive. The axial distances or edge lengths are A is equal to B is equal to C. The axial angles are alpha is equal to beta is equal to gamma, and totally it's not equal to 90 degree. Sorry, gamma is not equal to 90 degree. I think totally it's not equal to 90 degree, both are the same. So alpha is equal to beta is equal to gamma is not is equal to 90 degree. That's for rhombohedral or trigonal. And the examples for trigonal or rhombohedral are calcite, CaCO3, HGS, Cinnabar. And now moving on to monoclinic. For monoclinic, the possible variations are A is not equal to B is not equal to C. alpha is equal to gamma is equal to 90 degree, but beta is not equal to 90 degree. Examples are monoclinic sulfur, NaSO4.10H2O, etc., etc. And now triclinic crystal systems. The possible variations are primitive only. A is not equal to B, is not equal to C, alpha is not equal to beta, is not equal to gamma, is not equal to 90 degree. And the examples are K2Cr2O7, CuSO4.5H2O, and H3BO3. Okay, now we have the 14 Gravis lattices in the next table that covers the next two pages. So each lattice we have first one primitive or symbol, then body centered, face centered, unit cells of cubic lattices, all sides. These are the cubic lattices, primitive, body centered, and face centered. Now the description is that unit cells of cubic lattices, all sides of same length, are of same length, and angles between the faces are all 90 degree. Now we have primitive and body centered. And description given is unit cells, two tetragonal lattices, one side different in length to the other, two angles between faces all 90 degree. So first one was cubic, and now it seems like it's tetragonal lattices. Now the third one given is orthorhombic lattices with unequal sides. Angles between faces are all 90 degree. First one primitive and centered, body centered, face centered. The next is monoclinic lattices with unequal sides. Two faces have angles different to 90 degree. In the next section we have hexagonal lattice, which has only one figure. One side is different in length to the other two and marked, and two faces are 60 degree. And rhombohedral lattice, all sides are of equal length, and angles on two faces are less than 90 degree. Lastly, we have triclinic lattices with unequal sides A, B, C. A, B, C are unequal angles with alphabetic unequal angles with none equal to 90 degree. So that's basically what we discussed in table before. They have a descriptive approach with the figures given here. Now moving on to the number of atoms in a unit cell, this comes with derivations which we have to learn. We know that a crystal lattice is made up of very large number of unit cells, and every lattice point is occupied by one constituent particles, atoms, molecules or ions. Let us now work out on what proportion of each particle belongs to a particular unit cell. We shall consider three types of cubic unit cells, and for simplicity assume that the constituent particle is an atom. Primitive cubic unit cell has atoms only at its corner. Each atom at the corner is shared between 8 adjacent unit cells and is shown in figure 1.2. Sorry, 1.12. I got that wrong. 4 unit cells in the same layer and 4 unit cells of upper or lower layer. Therefore, only 1/8 of an atom or a molecule or ion actually belongs to a particular unit cell in 3 different ways. Figure 1.3, a primitive cubic unit cell has been depicted in 3 different ways. Each small sphere in figure 1.13a represents only the center of the particles occupying that position and not its actual size. Such structures are called open structures. The arrangement of particles is easier to flow in open structures. Figure 1.3b depicts space-filling representation of the unit cell with actual particle size, and figure 1.3c shows the actual proportions of different atoms present in a cubic unit cell. In all, since each cubic unit cell has 8 atoms on its corner, the total number of atoms in one unit cell is 8 into 1/8, which is equal to 1 atom. Okay, now we have body-centered unit cells. Body-centered unit cells BCC. The unit cell has an atom at each of its corner and also one atom at its body center. Figure 1.4a depicts open structure, and B depicts filling model, and C depicts the unit cell with portions of the atoms actually belonging to it. it can be seen that the atom at the body center wholly belongs to the unit cell in which it is present. Thus, in a body-centered cubic unit cell BCC, there are 8 corners, and 1/8 of an atom are shared to one atom in each corner. So in total it comes like 8 into 1/8 is equal to 1 atom is what a total BCC unit cell has as its own. Therefore, the total number of atoms present, and now there is one body-centered atom, so the total number of atoms present in a BCC unit cell is 2 atoms. Face-centered cubic unit cell. A face-centered cubic unit cell FCC unit cell contains almost all A face-centered cubic FCC unit cell contains almost all the corners and contains atoms at all its corners and at the centers of the faces of the cube. It can be seen in figure 1.5 that each atom located at the face center is shared between 2 adjacent unit cells, and only 1/2 of each atom belongs to the unit cell. Figure 1.16 depicts a open structure B space filling model and C the unit cell with portions of the atom actually belonging to it. Thus, in a face-centered cubic unit cell FCC, there are 8 corner atoms into 1/8 atom per unit cell. That's when we calculate the corner atoms. There are 8 corners, and now 1/8 of an atom is shared at each corner, which forms 8 into 1/8 is equal to 1 atom, and 6 face-centered atoms, and half of each atom comes in each face, so 6 into 1/2, which is equal to 3 atoms, and 3 plus 1 the atom that we got from the corners, and so total number of atoms per unit cell is 4 atoms. Now moving on, so 13 pages that we covered. Now we have a few in-text questions which we will take later on. Closed packed structures. In solids, the constant particles are close packed, leaving the minimum vacant space. Let us consider the constant particles as identical hard spheres and build up 3-dimensional structures in 3 steps. Okay. A is close packing in 1 dimension. This needs some visualization, which we won't be able to deliver through this video. So there is only one way of arranging spheres in 1-dimensional close packing structure, that is to arrange them in a row and touching each other. That's close packing in one direction. In this arrangement, each sphere is in contact with 2 of its neighbors. The number of nearest neighbors of a particle is called its coordination number. Thus, in 1-dimensional close packing arrangement, the coordination number is 2. Close packing in 2 dimensions. 2-dimensional close-packed structures can be generated by stacking, placing the rows of close-packed spheres. This can be done in 2 different ways. The first one being, the second row may be placed in contact with the first one such that the spheres of the second row are exactly aligned horizontally as well as vertically. If we call the first row as A type of row and the second row being exactly the same as the first one, it's also an A type row. Similarly, we may place more rows to obtain AAA type of arrangement, as shown in figure 1.8a. Okay, you can see the figure 1.8a at the lowermost end of the textbook, and on the next page they have said, in this arrangement each sphere is in contact with 4 of its neighbors. Thus, the 2-dimensional coordination number is 4. Also, its centers of these 4 intermediate neighboring spheres are joined, a square is formed. Hence, this packing is called square close packing in 2 dimensions. The second one is a second row may be placed above the first one in a staggered manner such that its spheres fit in the depressions of the first row. If this arrangement of spheres in the first row is called A type of arrangement and the second row is different and may be called B type, when the third row is placed adjacent to the second row in a staggered manner, its spheres are aligned with those of the first layer. Hence, this is also a A type of arrangement. The spheres of similarly of the fourth, one in the second row is in a different way and may be called B type. So first one was of A type and the second one is of B type. It's of a different type than the first row that we placed. When the third row is placed adjacent to the second row in staggered manner, the third row will be A type and the fourth row will be B type. So AB arrangement is formed in the second, that is two-dimensional hexagonal close packing. So this is hexagonal close packing. Before we talked about square close packing. We are skipping a lot of part here which is not of much importance. Okay. Anyways, we'll read that. Hence, this arrangement is of AB type. In this arrangement, there is less free space, and this packing is more efficient than square close packing. Each sphere in contact with 6 of its neighbors, and two-dimensional coordination number is 6. The centers of 6 spheres are at the corners of a regular hexagon. Hence, this packing is called two-dimensional hexagonal close packing. It can be seen in figure 1.18b that in this layer there are some voids, empty spaces, and these are triangular in shape. The triangular voids are of two different types. In one row, the apex of the triangles are pointing upwards, and in the next, the layers are downwards. Close packing in 3 dimensions. The next part is close packing in 3 dimensions. We'll read that also. All real structures are 3-dimensional structures. They can be obtained by stacking 2-dimensional layers one above the other. In the last section, we discussed close packing in 2 dimensions, which can be of 2 types: square close packed and hexagonal close packed. Let us see what type of 3-dimensional close packing can be obtained from these. The first one is that 3-dimensional close packing forms 2-dimensional square close pack layers. While placing the second square close pack layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. In the second layer is placed over the first layer such that the spheres of the upper layer are exactly above those of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally as well as vertically, as shown in figure 1.9. Similarly, we have one above the other. If the arrangement of spheres in the first layer is called of A type, all the layers have the same arrangement, thus the lattice has A type of arrangement. The lattice thus generated is simple cubic lattice, and its unit cell is primitive cubic unit cell. See figure 1.194, the visual approach. The second one in close packing in 3 dimensions are like hexagonal close pack layers. Okay, 3-dimensional close packing from 2-dimensional hexagonal close pack layers. 3-dimensional close pack arrangement. 3-dimensional close pack structure can be generated by placing layer one over the other. Octahedral voice of the next part. Okay, we'll just go by the text. The next is A. Placing second layer over the first layer. Let us take a 2-dimensional hexagonal close pack layer A. Let's take a 2-dimensional hexagonal close pack layer A and place a similar layer above it, such that the spheres of the second layer are placed in the depressions of the first layer. Since spheres of 2 layers are aligned differently, let us call the second layer as B. It can be observed from figure 1.20 that all the triangular voids of the first layer are not covered by the spheres of the second layer. This gives rise to different arrangements. Wherever a sphere of the different layer is above the void of the first layer, or vice versa, a tetrahedral void is formed. These voids are called tetrahedral voids because tetrahedron is formed when the centers of these 4 spheres are joined. They have been marked as T in figure 1.20. One such void has been shown separately in figure 1.21. I actually have not understood a single word from this. I hope you do. Well, I too am a student, so this is the best you can expect from me, from a student like me. Maybe you guys might be smarter than me. Who knows? At other places, the triangular voids in the second layer are above the triangular voids in the first layer, and the triangular shapes of these do not overlap. One of them has the apex of the triangle pointing upwards and the other downwards. These voids have been marked as O in the figure 1.20. Such voids are surrounded by 6 spheres and are called octahedral voids. One such void has been shown up separately in the figure 1.21. The number of these two types of voids depend upon the number of close-packed spheres. Let the number of spheres of the close-packed spheres be n, then the number of octahedral voids generated is equal to n, and the number of tetrahedral voids generated will be 2n. Placing the third layer of the second over the second layer, we have, when the third layer is placed over the second layer, there are two possibilities. First one is covering tetrahedral voids, that is, tetrahedral voids of the second layer may be covered by the spheres of the third layer. In this case, the spheres of the third layer are exactly aligned with those of the first layer. Thus, the pattern of arrangement is repeated in alternate layers. This pattern is often written as ABAB arrangement pattern, and this structure is called hexagonal close-packed structure (HCP). In this sort of arrangement, atoms are found in many metals like This type of arrangement is found in many metals like magnesium, zinc, etc. The next part is second type of placing third layer of over the second layer arrangement is covering octahedral voids. The next possibility while placing third layer over the second layer is covering the octahedral voids and the arrangement. The third layer may be placed above the second layer in a manner such that its spheres cover the octahedral voids. When placed in this manner, the spheres of the third layer are not aligned with those of either of the first or the second layers. This arrangement is called C-type arrangement. Only when fourth layer is placed, its spheres are aligned with over those of the first layer shown in figure 1.22 and 1.23. This pattern of layers is often written as ABC arrangement, and this structure is called cubic close-packed CCP or FCC structure. Meanwhile, such as copper and silver crystallize in this structure. Hexa or cubic phase. Both these types of close packing are highly efficient, and 74% of the space in the crystal is filled. In either of them, each sphere is in contact with 12 spheres. Thus, the coordination number is 12 in either of these two structures. Formula of a compound and number of voids filled. I think we almost end this sketch. You can see that. Oh shit, we have a lot of light. Imperfections. Anyways, we'll just read it over. Formula of a compound and number of voids filled. Earlier in this section, we have learned that when the particles are close packed, resulting in either CCP or HCP arrangement, two types of voids are generated. While the number of octahedral voids present in lattice are equal to the number of close-packed structures, the number of tetrahedral voids generated is twice this number. In ionic solids, the bigger ion, usually cation, occupies the void. If the latter ion is small enough, then the tetrahedral void are occupied. It's bigger than the octahedral voids. Octahedral or tetrahedral voids are not occupied. What the hell? I don't understand the word. In a given compound, the fraction of octahedral or tetrahedral voids that are occupied depend upon the chemical formula of the compound, as can be seen from the following examples. Then we have another example 1.1, which is a question, and we have in box thing that's containing tetrahedral and octahedral void. I think that won't be much important, as the exam this time would be liberal during this COVID scenario. Well, I don't understand a word after reading this NCERT textbook. I usually explore with the internet. I read articles. I have a Bible subscription, so that's the means through which I study actually. I don't know what I'm gonna do with this online classes going on. Let's see. Packing efficiency is the next part. In whatever way the constituent particles, atoms, molecules, or ions are packed, there is always some free space in the form of void. Packing efficiency is the percentage of total space filled by these particles. Let us calculate the packing efficiency in different types of structures. Packing efficiency in HCP and CCP structures. Both types of closed packing, HCP and CCP, are equally efficient. Let us calculate the efficiency of packing in CCP structure. In figure 1.24, let the unit cell, that's derivation, and at last we get the packing efficiency is actually volume occupied by the spheres in the unit cell divided by the total volume of the unit cell into 100. That's the universal formula that you can use all here to find the packing efficiency. And the packing efficiency for HCP and CCP is 74%. The packing efficiency for BCC is 68%, and the packing efficiency for simple cubic lattices is 52.4%. Now, the next we are moving on to calculations involving unit cell dimensions. I think that's not important. Anyways, we'll just read it. Maybe this can be important. I just supposing if it's important or not. I totally don't know anything much about the syllabus. I'm just reminding that I too am a student, and this is the first time that I'm reading the textbook. I'm just making these videos for the fun of it. I just wish I could improve my speaking through this process, so that's actually why I'm doing these videos. If you find these videos interesting, you can subscribe to my channel and also share my videos. I'm always happy to do that. And anyways, coming back, calculations involving unit cell dimensions. You don't subscribe, right? Also turn the bell notification on so that you get to know when I'm uploading a new video. YouTube has kind of reduced the reach, so you will probably get notified if you haven't turned the bell notifications on. From the unit cell dimensions, it is possible to calculate the volume of the unit cell. Knowing the density of the metal, we can calculate the mass of the atom in unit cell. The determination of mass of a single atom gives an accurate method of determination of Avogadro constant. Suppose edge length of a unit cell of a cubic crystal is determined by X-ray diffraction of AD. The density of solid substance is determined by the Suppose edge length of a unit cell of cubic crystals are determined by X-ray diffraction is AD. The density of the solid substance is M, and the molar mass, and M is the molar mass. In such a case of cubic unit cell, volume of the unit cell will be A cube. Mass of the unit cell is equal to number of atoms in the unit cell into mass of each atom, that is equal to Z into M. Here Z is the number of atoms present in one unit cell and M is the mass of a single atom. Mass of an atom present in a unit cell M is equal to M by Na. Na is the Avogadro number and M is the molar mass. Therefore, density of the unit cell is equal to mass of the unit cell by volume of the unit cell is equal to Z dot M divided by A cube is equal to Z dot M into A divided by A cube into Na, or D is equal to Zm by A cube Na. That's it. And now remember that density of unit cell is same as the density of the substance. The density of the solid can always be determined by other methods. Out of 5 parameters D, Z, M, and Na, if 4 are known, we can determine the fifth. Now we have example 1.3, which will take later on, and a few in-text questions, which too we will be looking later on. Imperfections in solid. Although crystalline solids have short-range order as well as long-range order in arrangement of their constituent particles, yet the crystals are not perfect. Usually a solid consists of an aggregate of large number of small crystals. These small crystals have defects in them. This happens when crystallization process occurs at fast or moderate rates. Single crystals are formed when the process of crystallization occurs at extremely slow rates. Even these crystals are not free of defects. The defects are basically irregularities in arrangement of constituent particles. Broadly speaking, the defects are of two types, namely point defects and line defects. Point defects are irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance, whereas line defects are the irregularities or deviations from ideal arrangement in entire rows of the lattice points. These irregularities are called crystal defects. We shall confine our discussion to point defects only. Types of point defects. Point defects can be classified into three types. First one, stoichiometric defect. Second, impurity defect. And third one, non-stoichiometric defect. A stoichiometric defect. These are point defects that do not disturb the stoichiometry of the solid. They are called intrinsic or thermodynamic defects. Basically, these are of two types, vacancy defect and interstitial defect. Vacancy defect. When some of the lattice sites are vacant, the crystal is said to have vacancy defect. This results in a decrease in the density of the substance. This can also develop when a substance is heated. Interstitial defect. When some constituent particles, atoms, or molecules occupy an interstitial site, the crystal is said to have interstitial defect. This defect increases the density of the substance. Vacancy and interstitial defects are explained above and can be shown by non-ionic solids. Ionic solids must always maintain electrical neutrality rather than simple vacancy or interstitial defects. They show these defects as Frankel and Schottky defect. Now, stoichiometric defect in the case of ions. First, we have Frankel defect. This defect is shown by ionic solids. The smaller ion, usually cation, is dislocated from its normal site to an interstitial site. It creates a vacancy defect, and at its original site, an interstitial defect at its new location. So, Frankel defect basically is caused when an ion is displaced from its original position. So, it creates a vacancy defect at the point from where it escaped, and then interstitial defect at the point that it went to. Frankel defect is also known as dislocation defect. It does not change the density of the solid. Frankel defect is shown by ionic solids in which there is a large difference in the size of ions. For example, ZnS, AgCl, AgBr, and AgI. Due to the small size of Zn2+ and Ag+ ions. That's why these atoms show Frankel defect. Now we are moving on to Schottky defect. It's basically a vacancy defect in ionic solids as Frankel defect. In order to maintain the electrical neutrality, the number of missing cations and anions are equal. Like simple vacancy defect, Schottky defect also decreases the density of the substance. Number of such defects in ionic solids is quite significant. For example, in NaCl there are approximately 10⁻⁶ Schottky pairs per centimeter cube at room temperature in 1 centimeter cube. There are about 10⁻22 ions. Thus, there is one Schottky defect per 10⁻16 ions. Schottky defect is shown by ionic substances in which the cation and anion are almost similar size. For example, NaCl, KCl, CSCl, and AgBr. It may be noted that AgBr shows both Frankel as well as Schottky defect. Impurity defect. If molten NaCl containing a little amount of SR2 plus SrCl2, we'll go once again. Impurity defects. If molten NaCl containing a little amount of SrCl2 is crystallized, some of the sites of the Na+ ions are occupied by Sr2+ ions. Each Sr2+ replaces two Na+ ions. It occupies the site of one ion and the other site remains vacant. The cation vacancies are unequal to the number of Sr2+ ions. Another simple example of solid solution of CdCl2 and AgCl2. I know I haven't understood a word. So idiot. Anyways, moving on to non-stoichiometric defect. The defects discussed so far do not disturb the stoichiometry of the crystalline substance. However, a large number of non-stoichiometric inorganic solids are known, which contain the constituent elements in which contain the constituent elements in non-stoichiometric ratio due to defects in the crystal structure. These defects are of two types. First one is metal excess defect and the second one is metal deficiency defect. Metal excess defect. Metal excess defect is due to anionic valencies. Alkali halides like NaCl and KCl shows this type of defect. When crystals of NaCl are heated in an atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the crystal. The Cl- ion diffuses to the surface of the crystal and combines with Na atoms to give NaCl. This happens by loss of electron by sodium atoms to form Na plus ions. The released electron diffuse into the crystal and occupy anionic sites. As a result, the crystal now has an excess of sodium. The anionic sites occupied by unpaired electrons are called F centers. From German word Farbencenter for color center. They impart yellow color to the crystal of NaCl. The color results by the excitation of these electrons when they absorb the color is a result of the excitation of electrons when they absorb energy from the visible light falling on this crystal. Similarly, excess of lithium makes LiCl crystals pink and excess of potassium makes KCl crystals violet or lilac. The metal excess defect is due to the presence of an extra cation at the interstitial site, and zinc oxide is white in color at room temperature. On heating, it loses oxygen and turns yellow. That's an example of metal excess defect. And ZNO, on heating, there is Zn2 plus half O2 plus 2E minus. That is the chemical equation. Now there is an excess of zinc in the crystal and its formula becomes Zn1 plus XO, and this Zn2 plus ions move to the interstitial site and the electrons to the neighboring interstitial site. The second one is metal deficiency defect. There are many solids which are difficult to prepare in stoichiometric composition and contain less amount of metal as compared to the stoichiometric proportion. A typical example of this type is FeO, which is mostly found in with the composition of Fe0.950. It may actually range from Fe0.930 to Fe0.960. In crystals of FeO, some Fe2 plus crystals are missing, and with the loss of positive charge is made up by the presence of the required number of Fe3 plus ions, and that's the end of the portion for the 2020 to 2021 syllabus. Like the rest of the part, like electrical properties and the next mechanical properties are deleted from this chapter, but the same parts are followed up in the next coming up chapter, that is semiconductors. So anyways, you don't have to study this part. This part is continued repeated again in the semiconductor portion. I won't say more study, it's your wish. My wish was I just keep this part. It was also deleted portion for us, but for you it depends on which year you are right now. I don't know how long YouTube will have this video. So according to which year you are, and they deleted, if there are deleted portions, these are deleted portions for you also, then you can skip this, or otherwise you can just have a read through it. There's not much. There are electrical and magnetic properties. So that would be the end of this video on the solid state. I'll be making another video on the next lesson of chemistry, mostly physics and biology. I don't know if I should be doing English. I'm actually of bio-Sanskrit stream, so the subjects I have are physics, chemistry, biology, English and Sanskrit. So anyways, I can't do Sanskrit videos. I barely know how to read Sanskrit fluently. I can't speak Sanskrit. Well, English we can do, but like it might be. Anyways, we'll think about that. I'll be doing videos on physics and biology also in this channel. So if you might be interested in my videos or if you like them, then feel free to subscribe. Also, every share will be appreciated, every like will be appreciated, even every dislike will be appreciated. So thank you. It's me signing off. Ta-da. Sorry guys.